Okay, here we're given a function and asked to identify any discontinuities and also look for vertical and horizontal asymptotes. All right, so let's take a better look at this. This is x squared minus x minus 2 over x squared plus x minus 6. So let me also get a factored version if possible. All right, this must be 1 and 2. Minus and plus, and this one must be minus 2 and x plus 3. Okay, so I can immediately see from the denominator of a rational function that I will have discontinuities at x equals 2 and x equals minus 3. Okay, but these are going to be very different. Okay, so let's see what we could say about them. We're just supposed to identify them. Let's go a little further. At x equals 2, notice that would be a canceling factor there. So we're not actually going to cancel it, but that would be a canceling factor. So that is a whole which is removable. X equals minus 3 gives us a 0 in the denominator, but not in the numerator. That's a vertical asymptote, and that is non-removable. Okay, so we've answered part of our questions here. Our last question, vertical asymptote is x equals minus 3. So now if we want to talk about a possible horizontal asymptote, that's where we have to look at the limit. So the limit as x approaches infinity, and the limit as x approaches negative infinity of this function. And I'll use the expanded form for this. Okay. Here again we have limits going to infinity of polynomial over polynomial. So we have just the battle of the powers. We tie, so I get a 1 over 1. I get 1. I get the same thing here. So that tells me I have a horizontal asymptote at y equals 1. Okay. Find constants a and b such that this function, this piecewise function, is continuous everywhere. Okay, so because each piece of this is just a linear function, I know that within each piece, I'm fine, I'm continuous. The only places that I have a potential problem with continuity is at the connection points. Okay, so I have to look at 1 and 4, and I'm going to have to ensure that it is continuous there. Okay, so let's take a look at x equals 1. Okay, the first thing I want to talk about is f of 1. Well, f of 1, that's included in that first piece, so f of 1 would be 3. The limit as x approaches 1, well, I'm going to have to do that from two sides. So I'm going to have to go from one from the left and one from the right, because from the left it looks like 3, and from the right it looks like ax plus b. Okay, so that would just give 3, but x approaching 1 of ax plus b would be a times 1 plus b, or in other words, a plus b. Okay, so that means if I want continuity there, I would have to have these things be equal. So I need a plus b equal to 3. That would give me the limit existing and equaling 3 and being the same as the function value. At x equals 4, f of 4 is included here, so 2 times 4 minus 8, or 0. Okay, but then I'd need to look at my limit. X approaches 4 from the left. Limit as x approaches 4 from the right of 2x minus 8. No. As x approaches 4 from the left, I'm in here. So this would actually be ax plus b. On the right, it would be 2x minus 8. Okay. So putting 4 in here, I get a times 4 plus b. So I get 4a plus b. Putting 4 in here, I get 2 times 4 minus 8. I get 0. So here I need 4a plus b equal to 0 to make these equal, giving me a limit of 0, then matching my function value as well. Okay, so I need those things true. So I'm going to need 4a plus b equal to 0 and a plus b equal to 3. If I subtract these, I get 3a equals, so I subtract, negative 3. I get a of negative 1, and that means a plus b is 3, so negative 1 plus b is 3. So that means b is 4. So I need a equal negative 1, b equal 4. That will ensure continuity everywhere for this original function.